start with lecture 16, and this will be mainly called ion channels 2. This is the second lecture on ion channels. And it will be mostly focused on models of ensembles of ion channels. Ensembles, okay. So remember, my previous class was on models for a single ion. So I was always thinking about channel that is either closed or open, and this opening and closing occurs stochastically. Okay, so it was the world of a single ion channel. If you remember well, I was giving a very simple model in this case, in which I had two rates. So this was continuous time, discrete states. This was the closed configuration. We got C, and this was open, and there were rates. There was a rate alpha in open to open a channel, and a rate beta to close a single channel. However, this is not the most accurate description of what happens in a cell. In a cell, you have to think that there are many ion channels. So you have a membrane, the membrane is large, and there are many of these. So you will have the full membrane of the cell, whatever it is. And here there will be many of these ion channels. Some of them will be open, some of them will be closed, etc. No? And we can think of this model, which I will explain later, as a case of n ion channels. So the number of ion channels is finite. And these are like gates that open and close in the same way this guy did. Okay? So this will be an ensemble of n systems, two-level systems like the one I was explaining in the previous lecture. Right? So before that, I was in the last class, this will be a recap of what I was discussing. I was discussing the one second. This is a recap of ligand gate versus ligand single. We were thinking about simple one channel that can be bound to a ligand. I remember we had, so we're thinking about a channel that has a receptor, and the receptor can be bound or unbound, attached to the channel. Okay. And we were saying that we had this reaction R plus L goes to RL with a free energy difference, which was epsilon. So in this case, we had RL divided by R times L. These are concentrations, remember, in units of 1 molar. Okay, it was E to the minus epsilon divided by kVt. It was called also 1 over the dissociation constant. Remember, when you have an exponential, remember the exponential has the argument of the exponential is dimensionless. Okay, so whatever that comes here should not have dimensions, so it should be dimensionless. So if you have concentration over concentration over concentration, these are units. So what you do is you express these three in units of 1 molar. So in reality, what this means is this one divided by 1 molar, divided by 1 molar, and divided by 1 molar. Okay, this is what this means reality. Okay, from here we found the following relation, which was about the following, that the fraction of occupied receptors, we are thinking about a cell that has n of these channels. Some of them are occupied, some of them are free. This was R tot. Remember, R dot is RL plus R. Okay, this is the concentration of ligand-bound receptors. This is free receptors. So these are like two types of ion channels. This was equal to L divided by L plus E. And what I explained in the last lecture is that this is a non-linear with the concentration of ligand. So it means the following, that if I plot the fraction of occupied receptors, it will be the fraction of open channels in this case, R dot is this as a function of the ligand concentration. This will be non-linear, and it will go something right. Okay, non-linear. It starts from 0. So of course, when let's say this is the picture, no? This is occupied, this is free, this is occupied, and this is free. Of course, when the concentration of ligand is 0, it means these circle molecules don't exist. They are all free. The fraction of occupied is 0. When the ligand concentration is infinity, there are so many of these molecules, so many that all of them get occupied. So this goes to 1 here, symptotically. And whatever happens in the middle is nonlinear with the concentration. This is what I was telling you before. Okay. So now, what I'll do is I will extend a little bit this model and complicate it a little bit. So now, instead of saying all of them are independent, I would say all of them are highly cooperative. So I will say the following: it should be cooperative. Which will be the following. And I will take an extreme example. Why I'm saying extreme? I say extreme because I will say the following. Either all of them are occupied or all of them are free. And what I would say is mainly the following. So now we have channels. Each of the channels has one receptor. Now, what I say is that each of the channels has n receptors. So instead of having this situation, I'll say that we have the channel, and the channel is more complex. So there is the membrane, this is the channel, okay, whatever structure it has. Okay, and then there are here receptors, and there are n receptors in each channel. And in order the channel to be open, all of the receptors have to be occupied. Okay, so for this gate to be open, the 3 have to be open, for example. Okay, so this is a receptor or channel. It could be a channel. And binding sites. And binding sites or binding receptors, if you want. In this case, the reaction is a very extreme example. So I'm saying either all are occupied or all free. So the reaction is something like this: R0 plus NL. R0 means all the receptors are free. And these are N ligands that come and bind. This becomes Rn, all the receptors occupied. And this is a reversible reaction. All right. So now look at this and compare to this chemical reaction. So what is the main difference? The main difference you can realize is that this reaction implies one ligand molecule. This reaction implies n ligand molecules. So when you write the law, this is called the law of mass action. Okay, when you write it, the law of mass action. For this example is the following. It is Rn. This is the this you can call it also RL, these ligands, okay, divided by R0 times, okay, I don't have space, I'm getting used to this situation. This is R0, and now it comes L, very important, to the power n. This is the way one writes the law of mass action here, okay? L to the power n, because there are n molecules. This is equal to E minus epsilon n divided by KT. This epsilon n will be the free energy difference between this state, where all of the receptors are occupied, and this state in which all are free. This is called epsilon n. And I call this 1 divided by K n. Okay, it's just a definition. Okay, so given this, one can repeat all the math that I did for this example. And if you repeat the math, the difference will be that wherever I have an L, there will be an L to the power n. It's the only thing that changes. So the equation that one gets is the following. RL divided by R dot, fraction of occupied, or fraction of open channel, because now we say when all the receptors are bound, the channel opens. This is, so the same thing as here, but I change L by L to the power n. L to the power n divided by L to the power n plus Kn. Okay. So the only difference is this n, and you can also write this equation as 1 divided, you can divide by L to the power n, numerator and denominator, and get 1 plus Ka. Sorry, Ka. Before I was calling this Kd. Okay, Ka. This is the way the book uses the notation. L to the power n. Okay. What is Ka? The Ka is the ligand occupation at half concentration. So I will draw now the curve and you will see. This type of equation is famous in chemistry and it's called Hill's equation. Hill's equation. And for example, the Michaelis-Menten theory has this type of shape. And what is important is when you take n equals to 1, you get this same structure. So this will be n equals to 1. And when you increase n, so when you make more and more cooperative effects, what you do is that the curve becomes sharper. This same curve that is here becomes much more sharp. So what happens is, comes, I think I have other color. Yes.
Sir.
Okay, 1 second. So if you take n equal to,
Sir.
give me a second. This will be n equals to 2. Yes?
Kn equals Ka power n.
Can you repeat?
I was asking if Kn equals Ka power n.
Kn, yes. Kn is Ka to the power n. Exactly.
Okay.
Exactly. It's a definition. Okay. Ka is K. Ka is, okay, Kn is Ka to the power n. Yes. Yes. But Ka is the concentration of ligand at which you are at the half. So this will be Ka. Okay. Is the amount of ligand concentration at which this becomes 1/2. Because if you put L equals Ka, this will be 1 plus 1 to the power n. 1 to the power n is always 1. So you get 1/2. Okay, you see it? Said?
Yes. Okay.
Yes, I have a question. My question is was that you are considering R as a recap and L as a ligand, and you consider pairing them as a chemical reaction
Yes.
that produces the RL, and the parameter R and L here are the rate of this chemical reaction.
Be careful. R is a state. So the receptor can be in state R or in state L. Sorry, in state R or in state RL. So what I'm thinking about is this is the receptor, okay, and this is the ligand. So when there is no binding, the receptor is in state R. It's this, and the ligand is in state L. So they are here. But then there's a chemical reaction that puts them together. And then this becomes the complex RL, which is this. Okay, now I think there are some rates for this reaction, but when you are in equilibrium, the concentrations of the free and L, and the bound, they obey some rules. They obey this rule in equilibrium. It's called the law of mass action. There are no rates here. The only thing is this, okay, here this is the free energy of the reaction. The energy of this reaction, okay, is the free energy of RL minus the free energy of R minus the free energy of R. This is this epsilon here. Okay.
Yes.
When you are in equilibrium, the concentrations obey this rule. So when the free energy is very negative, this is very probable, so it's more likely this than this. So this will give you this rule.
Yes.
And vice versa. So these are the concentrations. So how many of these are in a container, in a big container, and how many of these are in a big container? So this is what I'm plotting here. And this is what I'm calculating. This parameter, okay. So the main point is the following. The fraction of receptors that will be bound will depend, you have it in the picture here, will depend on how many in the container, how many ligand molecules are around. So if this concentration is very high, there are lots of these here, then this L will be very, very, very large, okay? And this is what I'm telling you. When L is very large, this is a number divided by infinity, so this is 0. Yes. And this will be 1 divided by 1, which is 1. So it means that the fraction of occupied receptors will be 1. All of them will be occupied.
I got, yeah. Thank you.
This is okay, because I was jumping between kinetic models with rates, and now I jump to concentrations, but it's just for you to see that there are many ways of attacking these problems. Okay. Okay. Other questions? Okay, so the effect of having 2 binding sites is to sharpen this curve. If I have 3 instead of 2, it becomes even sharper. So with 3, it goes like this, and then like this. This is n equals 3. Okay? And the bigger is n, the sharper and sharper it will become. So this will be a system which will respond very sharply to changes in the environment. Suddenly there is a little bit more, if you're here, n is very large, you have many cooperative effects, this will be like this, very, very sharp. So if you are below the critical concentration, all of them will be free. And if you make a very little change of concentration, this will jump. It will be like being in a critical point, okay? It will be when n is very large. And this appears a lot, okay, I lost my notes, but got excited talking to you. Appears a lot in those response problems, enzymatic reaction, etc. So this is very common in chemistry. Not everything is linear. This is what you should know. All right, all clear? Okay, I assume yes. So go to the next part, which is ensembles of channels. Of course, I started to discuss ensembles, but this is a very simple description of the problem. Now you know graphic processes, mark process. We can do something more advanced and live, and this is what I try to explain in the next part of the lecture. All right. So the next part is the following. So this will be called the birth death model of independent channels. Anyone knows what is a birth death model? Have you heard about this in your courses? I'm sure you will, or you have. Not in the course of evolution and ecology. You didn't? Okay, when you have a set of individuals, so let's say you have, I don't know, 20 individuals, and all of them are independent, and each of the individual has a certain rate to reproduce, so it becomes 2 individuals, but it has a rate also to die. So you didn't hear about this type of models? Okay, this is called birth and death. Okay?
You have.
Okay, there's someone who says yes?
Yeah.
Okay, that's good. So one can use this type of models, birth death, in the context of channels. And what I will do is the following. So remember, this is my the model of the model, because it's the, okay, you have C and you have O. So when we have one channel, we say the opening rate is alpha and the closing rate is beta. But now we are thinking about an ensemble. So we have a cell, and there are, okay, I don't know what is the best. Okay, there are channels, and some of them are closed, some of them are open. The distribution is stochastic. So the only thing I will say is that we have a cell which has n identical and independent two-state ion channels. What do I mean by this? I mean that the cell has n of these models. So every gate that I put here is one of these, okay? All of them has a rate alpha to be open and a rate beta to be closed. And all of them are independent. So this is the perfect model to be discussed with master equations, right? Because now we can discuss what is P of NG, which will be what is the probability that n channels are open in the interval t plus dt. Okay, right? So you can think about it in different ways. We can do very different models, but we would like to know this quantity, okay? So I have big n channel, amount of channel. This is finite. And small n can be 0 or can be 1, can be 2, can be 3, up to n. Right? This is the assumption of the model. And the way in which I will think about this model is something like this. So remember, when we think about Markov process, we have this representation of states. So now my variable will be small n. Before I was talking always about x, but now it will be small n, which is a natural number. So I'll have the following representation. This will be state 0. In this state, all the channels are closed. And then one channel can be open. So I can go to state 1, in which one of the n channels is open. This goes with rate omega plus 0. Okay, this is the way we define rates. But you can also close that channel and go back. This will be omega minus 1. Okay, this is the notation. When I have one channel open, I can open a second channel. 2. And this will go with rate omega plus 1. And you can close that channel with rate omega minus 2. Okay? And now we go on. So we have 3. And so on. Go to 4. Dot, 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 up to state n. And returns. So you go from here with w plus 2, w plus 3, and you reach this state with w plus n minus 1, because you come from state n minus 1. Closing channels, minus n, w minus 4, w minus 3. Okay, this will be our model. Any doubt, question?
You are considering that each channel is dependent on the state of another channel. At first you considered all of them as being independent, but here you are saying that I can open the channel second if the channel 1 be open. Yes?
I'm saying that all of them are independent. So I have n channels, and any of them can be open or closed equally at the same time. But if I have, for example, 5 open, in a very small time dt, the only thing that can happen is one of them opens or closes. Right? But it could be any of them. That's what I mean by independent. So imagine, okay, let's do the side model, okay? This will be the model. It's a cell like this, okay? And then there are 3 gates. It's this one, and this one. Okay? And now, let's say there's one channel that is closed. Now, what can happen next? In a very small time, either one channel opens or one channel closes.
Mm-hmm.
Okay? So if one channel opens, it means it must be this one. Right?
Yes.
It can happen this. And now, the 3 channels are open. It could be also that one channel closes.
Mm-hmm.
But any of them, okay, this cannot close because it's closed already. But this can close or this can close. So you can go either to this one or to this one. Okay. This one, okay, this belongs to state 1. Sorry, this is this is two channels open. This is state 2. Okay.
Yes.
State 2, you can go to state 3. These are the 3 channels open. Or you can go to state 1. This is 1 channel open. Okay.
I got now the states difference. Yeah. Thank.
When you have doubts about this type of models, the best is okay, I'm doing this very general and very, very, very abstract. But the best to understand these models is to put one example with n small. That's it.
Yes.
When,
Thank you.
okay, one thing. When n is 1, you recover this model. Okay.
Yes.
Okay. So with this, I think you got the point. I will do the math very general, but then, okay, one very important point is that you should realize that here there are 2 options, and yet there's 1. So the rates, in order to make sense, should depend on the number of channels that are open. So what we will pick the following. We will take omega plus n. Okay, omega plus means opening. So it's like if when we go like this. So in order to open, the different possibilities that can lead you to here depends on how many channels were closed. If there were 2 configurations with closed, it would go in 2 ways here. So this opening probability will depend on the number of closed channels. It will be something like this. N minus n alpha. Okay, here, big N is 3 channels. Small n, number of open channels, is 2. So 3 minus 2 is 1. So there will be a rate alpha. This makes sense because this is just opening 1 channel. Fine. And now the closing will depend on the number of open channels. Omega W minus n will be something like n times beta. This is the number of open times the closing probability. Look at this. Here there were 2 open. Each of them has probability beta to close. So there is beta and there is beta. So this will be 2 beta. If you come here, small n is the number of open channels. There were 2. So this gives you 2 beta. So this model is very, very, it reconciles the model for 1 channel we talked about before, and it extends to many channels. Okay, keep this in mind. I think this figure is good. I didn't have it last year, so now I understand better the model. This will be our assumption, that these rates, and look at this now, this is the power of what I was teaching to you of my process. I can do theory with omega plus n and go on, and now put here whatever I want. This is one assumption, which makes sense, but I could have chosen other rates. But this one, I think, makes sense. Okay, so now I know this is the model, and of course, when you give a model, you have to give an equation to describe its dynamics. And the equation is nothing but the master equation. So we do master equation. This model is as follows. Okay, so this is our object. What do you want to know? Partial t, p of nt will be, so you can, we go to one of them here, and we'll say, how can I change the probability from this state? So first of all, I can open 1 channel and get out from here. Sorry. First of all, I can gain probability. So I will first count this one. Okay, so this is opening 1 gate from the previous. This will be omega plus, I mean n, 2, so I count from n minus 1. N minus 1 times p, I come from n minus 1, so I have to put here n minus 1 t. I also have, okay, this is an incoming, I can also come this way. I come with omega minus of n plus 1 plus omega minus n plus 1 p n plus 1 t. This is the gain terms to the probability for state n. And then I have loss terms. I use this way and this way. So I lose from, okay, there's a minus here, minus. I lose from P and T, and the rates at which I lose is omega plus omega minus n. This will be omega plus n plus omega minus n. And listo. This is the master quiz for the model. Okay. If you solve this, you can get the probability to be with n open channels at time t. But of course, this is not a simple equation to solve. Okay. This is must realize. Okay. Now my question is this all? So is this correct? Or do I need to add something else?
Yes.
For the case of
No, because the case of 0 and n.
Yeah, exactly. So here, if I do the same game here, fine. But 0, be careful, because in 0, you don't have this rate. And you also don't have this rate. They don't exist. Also in n. This one and this one don't exist. So this equation is true for n greater than 1 and smaller or equal than n minus 1. Okay. So if you want to make this perfect, you have to add the boundary conditions. And the boundary conditions, the boundaries, we have at 0. So if you want to know partial t, p 0t, is you can say that you have one loss, one gain term from 1 plus 1 t 1t minus a loss term from 0 w plus no, sorry, this is minus this is plus 0 p 0t, and in the boundary n is similar. E n t equals so I have a gain term from n minus 1 w plus n minus 1 t n minus 1 t plus sorry minus omega minus n e n t. This will be a complete master equation with all the boundary terms. Okay. You can solve this, you will get all the statistics at finite time t for the problem. All right. So now there are many questions on how to solve this model. Of course, solving this will be very, very challenging, I tell you. It's not something you can do at once. Okay, I don't know what time is it, but I believe solving this model exactly will take me the rest of the lecture, probably. But I can give you the explicit solution. For a second, okay. 1 second. All right. All right. Okay, so you follow me until now, no?
yes.
Okay. This is the master equation. What I will do now is try to give you a solution for this problem. And you will see that at the end, it all makes sense with intuition in this. But probably you will see this model again in population, evolution and ecology course very soon. But there are different ways of solving it. All right. So first of all, let me ask you a question. That is, I go back to the model. 0, 1, if that works. You can ask, what is the current through this link? So let me just current. The probability current. So who can tell me how can I write the current in the stationary state? So first of all, let me tell you one thing. I will solve now the stationary state, okay? Stationary state. So I'd like to know what is P stationary n, which is the limit when t goes to infinity of P and T. Okay. So imagine I have the cell with one channel open, this starts opening, closing, and I look at a long time, what is the fraction of channels that are open and the fraction of channels that are closed?
Shouldn't it be zero? The
Zero.
current.
Yes,
Yeah.
exactly. Zero, because it is a line. So in the end, particles will start, if you think about a particle jumping, they will start jumping left and right, but in the end, the fluxes will balance. We are in a line. So this is like the two-state model that has no current in steady state. In this case, it is the same. If I have this in a ring, there can be current. There's no rings now, there's no loops, so the current is zero. And for conservation of currents, this current, which is zero, is the same as here, the same as here, is the same as here. The current is zero. So at zero, the current through zero is EST0, the rate to the right, which is W plus C, minus EST1, W minus 1. Okay, this is the net current from 0 to 1. But we know that this is 0. 0. So from this, we can solve PST1 in terms of PST0. PST1 stationary is PST0 times omega plus 0 divided by omega minus 0. That's it. So we have 1. Right? Now I can repeat the same thing here. So instead of looking 0 to 1, I look 1 to 2. And I will get PST2 will be PST1 omega plus 1 omega minus 2. Okay, I made a mistake because this was 1. I close 1. Okay. So this is repeating the same thing, but in the second link. And now what I can do is this PST1, I take it from here. So I put this formula here, and this is PST 0, omega plus 0, omega plus 1, divided by omega minus 1, omega minus 2. So one gets like a PST2 is PST0 times this and this. PST3 will be 3 of this, etc., etc., etc. So following this rule, one gets that P stationary n will be P stationary 0. And then when this is 1, we have one product. When it's 2, it's 2 products. So it's a product from m equals 1 to n of omega plus n minus 1, then omega minus n. This is the structure of the product. Okay, so up to here, I haven't solved the problem. What I have done is what is the stationary probability to be in state n in terms of the stationary probability of state 0 and the rates. So if I give you the rates and you can solve PST0, you can solve all of them. That's what this formula is telling you. Okay, and now one could say, how can I get PST0? Okay, so this is a tricky thing, but what you can do is you can impose normalization. You have normalization. How does the normalization condition look here? Anyone can say? Maybe.
I'm sorry, could you repeat that?
How does the normalization condition write for this case? We have this distribution, PSTN, right? When I tell you it's normalized, what does it mean?
The sum
Sum should be equal to 1.
n should be 1.
Or indeed, yeah, discrete.
Now it's sum because n is discrete.
Yeah.
And what is the n running from?
From 0 to big N.
Exactly. The channels can be all open. Sorry, all open, all closed. That's all you can have. Okay. Okay, so this should be 1. Sorry, 1 should be equal to this. This is the normalization for condition for this distribution. Okay, and what is this? So we know this is PST 0 plus the sum of all the rest. And the sum of all the rest is PST 0, the sum of this, the sum of n equals 0 to n of this guy, which is product of n equals 1 to n of omega plus n minus 1 divided by omega minus 1. Okay.
No, the sum starts from 1.
Sorry, the sum, yes,
Start from
now,
1.
exactly. You are being very, very clever here. The sum here starts from 1. Okay, because I have written this sum as PST0 plus the sum from n equals 1 to n. Okay, so this looks nice, but still it's not that nice because it's 1 equals to PST0 times this. So one can, the nice thing is one can solve PST0 here because PST0 is 1 divided by 1 plus this. So it is 1 plus the sum n equals 1 to big N, the product of n equals 1 to small n of omega plus n minus 1 omega minus n. Okay, this to the power minus 1. Okay, so 1 is equal to PST0, parentheses 1 plus all this. So PST0 is 1 divided by all this. So it's 1 plus some product of this to the power minus 1. Okay, you follow me with this?
Yes.
Okay. So now, given this, you will say, wow, this is nice, but I have a product and a sum, and I have to be able to solve this. This, in general, we cannot solve this. But in the model I'm telling you, we can do it. And this is not trivial, but you need to sit down and check, because this is a bit algebra. So now I will say that omega plus n, as I said before, is n minus n alpha, and omega minus n is n beta. When you take this and put it here, this simplifies a lot. And what you can see, if you check is that first, when you have this, you can find that, first of all, you need to know what is this ratio, omega plus divided by omega minus. So you can see that omega plus m minus 1 divided by omega minus m, this is what appears in the product. This is just n minus m plus 1 alpha divided by n beta. Okay, this is just, I take this and I replace it, okay? But now, when you have this type of products, you will see that you will have m, then the next will be n plus 1, then n plus 2, n plus 3, n plus 4. This will be this, and the next, and the next, and the next, and the next. The structure of this product will be like factorials. Because I'm multiplying, for example, in the denominator, will be m, then n plus 1, then n plus 2, n plus 3, n plus 4. And here the same. So this is the structure of a factorial. So it turns out, you can check yourself, please check, that this product that I have here, omega plus n minus 1, omega minus m, this is
n factorial.
beta to the power n factorial divided by n factorial n minus n factorial. Okay, it is not so trivial to find this, but you can do it yourself. Maybe Idris, you have a trick. But it becomes this thing, okay?
No, because it is like the micro-canonical ensemble. So you will have like the coefficient that n factorial over n factorial n minus n.
Exactly.
It's like a two-level system.
Sorry?
It is like the two-level system.
Yeah, it is like binomial coefficient here.
Yeah.
So all this here, this is equal to this. Okay, but then I have the sum. So when I go through on this, what I find mainly, okay, give me a second because I have to remember this, because then you have this product, and then you have this, you have the sum. So you can find that in the end I will do this sum, and I can extend the sum from n equals 0 to n, and this will be like a plus b to the power n. When you make a plus b to the power n, this number appears. This is the n chooses n, the combinatorial number, and then the powers appear. So just a little bit of algebra on this, and what you find out of this is, what you find out of this is the following, that P st n is okay, give me a second. Give me a second, because oh, okay. Sorry, I was with PST0. I'm here. So this is PST0 is 1 plus the sum n equals 1 to big N of alpha divided by beta times n chooses n to the minus 1. Okay, and what is this? You can write this as 1 plus this. Okay, this I forgot something. Okay, like this. Yes, so this is nothing but 1 plus alpha plus beta to the power n divided by beta to the power n, if I remember well, minus 1 to the power. Right? these two cancel. So this becomes beta divided by alpha plus beta to the power n. Okay, and now who remembers? So I'm saying PST0 is a quantity to the power n. Who remembers what was this? Beta divided by alpha plus beta.
It was one of the stationary states, I think, that we did for another model.
For the one-channel model,
I'm sorry, from a master equation in which we had a matrix of alphas and betas. The two-state model.
yes,
Yeah, the two-state model.
the two-state model. So the two-state model,
Yeah.
which is the building block of this model, you have the closed and the open. And this is open is alpha and closed is beta. The stationary, P open stationary, was beta divided by alpha plus beta. This
Yes.
is the probability for one channel to be open. So sorry, this probability for one channel to be closed. Closed. It's zero. It closed stationary. So the probability to have 0 channels open can be written as the probability of one channel to be closed times the probability of another channel to be closed, another channel to be closed. So this is the same as the probability to be closed stationary in the one state model to the power n. Okay? Is beta divided by alpha plus beta, we saw in the previous class, is the probability for a single channel to be closed. To have 0 open channels, all of them have to be closed. So this is one close times another close times another close times another close. They are independent. That's why we get this. So this makes sense. This makes sense. Now, okay, we are almost done because we have PST0, and this was the only thing that was not letting us calculate these things. So now I recall that PSTN, okay, you have to trace back because this is not so easy, is PST0 and alpha divided by beta to the power small n, and then n divided by. Now, you pick this, put it here, and it becomes something very nice and recognizable. Okay, because what one gets is nothing but the following: beta to the power n, big N, beta to the power big N, alpha n, beta n, n versus n. Then, okay, let me clean a bit because this is not big. Blackboard formulas. Okay. This is beta to the power n, beta to the power small n. So this becomes, okay, first I take the alpha to the power n, beta to the power n minus n, alpha plus beta power n times n divided by n. And this should remind you to something because I can write this as alpha divided by alpha plus beta. Sorry. Let me start with it. N divided by n, alpha divided by alpha plus beta. Alpha divided by alpha plus beta to the power n, and beta divided by alpha plus beta to the power n minus n. And remember, this was the probability to be closed. So this is 1 minus the probability to be open for a single channel. And this is probability open. So this becomes, interestingly, n to the n p0 to the power n, 1 minus p0 to the power n minus n. What distribution is this?
Binomial.
The binomial distribution, exactly. The binomial distribution, very nice. So all this crazy math gives me something that we could have got directly, because we said they are independent channels. There's a probability to be open, P0, and then you have, this is the binomial distribution. What is the probability out of n, out of big N, that small n are open? Is the binomial. So this makes sense. This is the binomial distribution. Great. So it is like the probability that small n out of big N channels that are independent to be open. So this is the Bernoulli trials with success probability is zero. Nothing else than that. All right, so with this, I'm almost done with what I want to explain. From here, we can also compute moments. So one thing we could do, for example, is the mean, the variance, or the end moment, k moment, better, or the variable. Okay, so how can we get this? In the end, if we want the mean, we should do mainly the mean of a Bernoulli. But now you know the Bernoulli, then that's it. How can we calculate the mean? So we have the distribution, PSTN, and then we have to multiply by n, and then sum from 0 to n. Okay, this will be the mean. The second moment will be like this. The kth moment will be, here we put k. So at this point, this will be, for example, you want to know what is the average number of open channels in a cell. So you have this, and then you multiply this by n, and you make the sum. So you could do this by hand, like do this sum. But now I'm going to show you a trick to solve this type of things, which is the generating function, which maybe you got to know. But it's a good trick to calculate this. Okay. So this is our main result. So let me copy here, and I'll show you the trick of the generating function, which I think is really good. Because especially in this type of models, where it's discrete and you have birth and death. Right. So let me copy here the distribution, stationary distribution, and which is n to the n p0, and 1 minus p0, big N minus n, and p0 alpha divided by alpha plus beta. Now we go into showing the trick. I want to try to you. Maybe you used the generating function before. I'm aware that for sure you did in another course. So how can I define the generating function here? Any idea?
You have to add the sum.
Add the sum. So generating function is, we have PSTN. And what do we have to do? Remember? It's like a Laplace transform, more or less. So we have sum over n. Now we go to a new variable. The variable is not n, it's something else. Okay?
K, you can call it K if you want.
call it K. I will call it Z because in my notes I have it as Z. So
Okay.
we will sum over n. So we get out of this variable.
You're going to multiply.
We can
Z.
use Z to the power n.
Yes.
Okay. This is what I would call the generating function gamma of Z defined like this. Okay. And now Z can take any real number because I can put here 0.1 to the power n, for example, or -1 to the power n. So just be careful that Z is a real number. Okay. All right. So the nice thing about generating function is it's very easy to calculate here. So the generating function is the sum, okay, the sum over n equals 0 to big N. Now I copy what I have here, and over n, I have set to the n with b0n will be set b0 over n, and then 1 minus b0 to the power n minus n. Why this is nice is because this is again the binomial formula. So now this will be equal to set p0 plus 1 minus p0 to the power n. Very, very simple. This is nice. So this is set minus 1 p0 plus 1 to the power n. Right. So this is it. You see that this distribution looks very ugly in terms of n because it's full of factorials, full of whatever. But the generating function is in terms of set, it only appears here. So it looks nicer mathematically. Okay. Here the n appears everywhere. N factorial, n minus n factorial, again here, again here. This has simplified the problem because set is only here. All right. So what can I do with generating function? Generating function, it is called generating because it generates all the moments. We can easily calculate all the moments. First of all, something very trivial would be what is the generating function at 0?
Should be 1.
Generating function at 0, actually, generating function at 0 is 0.
It is the normalization condition.
Should be 1.
No,
It should be
generating function at 0 is 0 because set to the power. No, okay.
No, it is 1
Yeah.
Because Z power 0.
because of the n equal to 0.
Yeah.
Z equal 1 is 1 to the power n, so it's the normalization. I should get 1.
Yeah.
So if I put equals to 1, this is 0 times, okay, this is 0, 1 to the power n is 1.
Yeah.
Okay, fine. And now I can do something a bit better. That is the following. I can take the derivative with respect to Z, the generating function. So I take the derivative here, and this is the sum, n equals 0 to n of, I take the derivative in Z. So this is n Z n minus 1 p st n. Okay, this is the definition of the derivative. And now, if I evaluate this in Z equals to 1, you see, when Z equals to 1, 1 to the power n minus 1 is 1. So this becomes, when Z equals to 1, this becomes n. You see, no? Okay, we haven't been so clear. When Z equals to 1, this sum becomes the sum n equals 0 to big N of n p s t n. And this is average n. So this means that I can compute the average by taking the derivative of the generating function with respect to Z and evaluating it at 1. So I have this function, I make the derivative with respect to z, and I evaluate at z equals to 1, and it is very easy because I take the derivative, the n comes down, z equals to 1, this goes to 0, so it's just basically this p0 comes out, so it's n p. Very simple. And this is very intuitive. We have n channels. The probability for a channel to be open is p0. The average of open channels is the total number of channels times the probability for each of them to be open. Nothing is okay, simple. But you see, it's very elegant with the native function. And one can go further and show that, okay, I will continue here. One can show that if you take two derivatives with respect to z, there will be n, and there will be also n minus 1. So one can show that n times n minus 1, the average of this quantity, is the second derivative evaluated at 0. 0, not at 1. Be careful with this. When you do this here, one derivative, another derivative, evaluate at 0, this becomes n times n minus 1 times p0 squared. This is just algebra, you can see. And now, from these two, you can compute the variance, because the variance of n is n squared minus average n squared. Here you have n squared minus average n. Here you have n. So with these two you can do it. And this becomes, you do a couple, okay, this is, okay, let me just write something here. For this, what I use is n minus 1. This is n squared minus average n. Then I sum average n. And I subtract average n to the power 2. Okay, so I'm using this one plus this one minus this one to square. And this gives me n p0 1 minus p0. This is a well-known result from the Bernoulli. So it means that the fluctuations, the values of n goes like n. So the fluctuations, which is the standard deviation, goes like square root of n. Okay? This model. So what this implies. But of course, you can also go to a table and now also you can also sum here to n squared and go on. This is just a trick I'm explaining you to simplify things in some examples. All right, so I think with this, I'm done with what I wanted to explain today. So please let me know if there are questions. Of course, the math I was read fast, but it's good you recap, you check your notes, you check in the book as well, the reference. But I believe this makes sense in the way we constructed the model from one unit to n that are independent. All right, and the nice thing on the next lecture is I will connect this also to Fokker-Planck. I was telling you there are models that are discrete, models that are continuous, and the Fokker-Planck we say is that we will do an approximation that transforms the master equation into Fokker-Planck in this case. Right, so any questions?
I have a question.
Yes.
I have a question with the mean of n times n minus 1.
Yes.
Shouldn't be evaluated at 1, not 0?
I think it's at 0 if I remember well. You take one derivative, n minus 1. You take another derivative. Yes. take one derivative, you have this. Now you take the second derivative, so it will be n minus 1, z n minus 2.
Yeah.
And then what you want is that, so if you put z to 0, there is n minus 2. I think you have to be careful from where do you sum. This is very important. And you have to be careful because, okay, because you start from n minus 2. Okay, I have to revise this, but I think it's at 0. Because if you put 1,
Should
no, the point
I think it's equal to is 1 also.
1?
Evaluated in 1.
you have to be careful on one thing. Yes, I think it's 1 because you have the second derivative, n minus 1, z equals to 1 to the power n is 1, and then you have n minus 1 and you sum it. My only doubt was about the boundary terms, because you start from n0. I'm not so sure, because I think
it should be also 1.
okay, we have to check this. It could be I made a mistake here, but I remember checking this, and it was 0. Okay, let's check this in detail, because I think if you have 1, you take the derivative, you sum from 0. You have to be careful. 0, okay. I think it is 0, but
It's because it's 0, the derivative is just the sum of all 0. It must be 1.
if it's that 0, yes.
Mm.
Yes.
Or no.
Must be 1. I think let's take here. Yes. Let's double check, but it's true that if you put z equal to 0, you're not summing. Yeah. You're summing zeros for n greater than, yes, this must be 1. Yes. I think this is an error I had in my notes, typo, and this is also in the book, so be careful with this. Must be 1. Yes, actually, yes, because then if you put 1, you have the 2 derivatives, n minus 1, and then you have to kill the z. So it must be 1, yes. Yes, so please correct this. Any questions?
Excuse me, can you tell me how you build the generating function?
Generating function is defined like this. This is defined, okay, it's a sum where n. So PST has as an argument n. Now, this is kind of a Laplace transform, okay? When you do the Laplace transform of a time-dependent function, it becomes a function that depends on a frequency. So you have to multiply by something, you're summing on n. So you get rid of this argument n, okay? And there's a new variable set here. So it's like a Laplace transform of Fourier in Z. This is the definition. And what I'm doing is I put PSTN from the solution we had here when I sum. So it's Z to the power n, which is this, and all this here. And I'm summing. You see?
Yes. I'm okay with all of the rest, but just for that we put the PST there. I was thinking about that, how we put PST there.
Yeah, well, you have to sum it, but PST you have to put what you get as PST, which is this function. This is function of n, okay? Okay, you put this here, and in the sum becomes this.
Yes.
All right, and this has a structure of a this is the binomial formula. A, if you do A plus B, okay, this is A, and this is B. A plus B to the power n is A to the power n, B to the power n minus n times the binomial coefficient.
Yes, thank you.
That's why you do this. Okay.
Yes, thank you. Thank you.
Other questions? Okay.
No.
Please. No questions? Or there was a question? I got confused.
I just want to ask as a summary. So is this this here the mean of n? So given a system or a cell with n ion cells, this is the mean of having open.
Yes, so you have the cell, there are big N channels.
Yeah.
And what is the average number of open channels in the cell?
Yes.
Okay, this means you will have a cell with N channels, another cell with N channels, another cell with N channels. You do the histogram of open channels in each of the cells. And the average of open channels among different cells is this.
Okay. And the variance is, so we say that the number of open channels follow
is the variance of the number of open channels, because the number of open channels is a stochastic variable.
Yes, yes.
So you measure the number of open channels, it is stochastic. Different cells will have different number of open channels. You build a distribution, and the variance of this distribution is linear with n. Okay?
Okay.
The more channels you will have open, the variance will be larger. There will be more fluctuations. This is what it means. Okay. If you want in the next lecture, I do a sketch of all this in a cell, so we go back to the biophysics, but today I gave you all the full math. This is one of the most complicated models I'll explain in the course. But this is about, okay, actually you can do a test, you can plot this distribution, verbally like this. You will have a mean and a variance that depends on the number of open channels. I think, but I don't remember very well. I think distribution like this, so it has some width. Yeah. Of course, it's a positive. It's not a Gaussian because it cannot have negative values. But there is an average value. There is a distribution. This is n. This is P of n. And this distribution will depend on what are these alphas and betas. It will change. Okay. Right. Other questions? Okay. If not, finish here. I hope you enjoyed this new setup. Let's see how the recording has gone. It's the first time I record the lecture this way, so we'll see. But we meet again on Thursday. Right.
Okay, thank you.
Thank you.
Thank you.
Thank you. Bye.
Thank you.